we're gonna talk about the by sensor again. Yeah, and we continue to discuss the details, explore some details about the by sensor and what is by function and what kind of the materials and what is the mechanism. And we continue to watch the movie, and during the movie, we elaborate on some details and some mechanism. So first one, let me stop my video and share my screen. Yeah, so first and in the last lectures I also mentioned this one. Oh guys, yeah, this week of the March 29, this week we should have based on your previous homework, I need you a little bit specific objective and to be done this week, each one or two sentences to expand this part. And the background information, please expand to 2 pages. And materials method, I need 1 page to be done this also this week. And please put a little bit expect results, half page. And the significance around half pages. So I already post this part in your homework. I mentioned that this one is a teamwork. So any students, any questions for this part? Yeah, so I wish you guys before tutorial this Friday you can send to me, and I could give you a comments, then submit on next Monday. So besides this one, as we talk about in the last lecture or some part of movies, we talk about is the wearable sensor. So wearable sensor, I definitely can use this one in the heart, brain, or blood vessel. This one definitely, and robot again. Yeah, you need a wearable sensor in your stent vesicle graft inside. And basically to detect what is a biological signal, could be physiological, some enzyme, protein change, some enzyme. That's we talk about the lactose or the glucose. There's enzyme change, and some chemicals we generally say is a redox reaction. So that's very similar to chemical electronic chemistry. So that's leading to the voltage change or electron moving, so leading to the current change and the voltage change. And the mechanical is like stiffness and the movement. Stiffness become some movement, for example, it's like joint movement, heartbeat. For example, it's a heartbeat. And by compatible, that's we already know, that's by robot. So by robot definitely with all kind of sensors inside by robot. So it could be the chemical, biological, physical, a lot of things, and take pictures. And the materials requirement we already know, right? By compatibility. And the mechanisms is resist the change. For example, it's like this one generate a piece of materials, conducting materials, leave the conductive with resistance. However, if mechanical deformation happens, so change it to R1, R2. So we know what's inside, in the body. Changes in the mechanical, for example, deformation for the bone, for the heart, and for muscle, muscle, bone, a lot of things, skin. So we know resistance change and voltage change, electronic chemistry. That's actually also where finally is the voltage change. And so here's like a huge applications is right now is for glucose to detect, and from like sweet, okay, and also in the under the skin, so the skin pen penetration of the skin using microneedle, or like this one, or patch. So it could be like a patch or microneedle together. Like this one. We know have a lot of fluid in the skin. So if you design a microneedle, so we can detect the signal change. That's the one way. And so let's watch the movie first and take a look at it. Where's my interesting? I think I put it there. Yeah. Can you guys see my screen? I want to confirm before the movie. Any students can make a confirmation to me?
Yes, we can see it.
Okay, thank you.
On, for example, clothing, my biggest concern would be the first time the clothing got washed. It's not really going to.
So this one is like what limitation electrochemical glucose, but the glucose sensors basically we have different materials, could be on the PCB board or wash cycle on the sensor. You can on the fabric, but you need to careful about the wash cycle. So the ones like for the biosensor or like the glucose sensor right now, it's a lot of more focus on polymer based glucose. So this polymer based, that's like Professor Joseph Wang from UC San Diego, and his lot of works focused on biorobot. We have another movies, specifically, that's like his presentation in Harvard, Harvard University. It's about robot and sensor. We will talk about this one. So glucose sensors using polymer is one of the most popular way, and biodegradable or biocompatible, flexible, or polymer can make it.
And you can also make glucose sensors on paper, electrochemical glucose sensors as well.
Oh,
they're sensors, and you should definitely not be turning for health. I know that there's some people online with glucose sensors as well. You can detect glucose obviously in the blood. That's happened for 40 years. You can measure it in what's called the interstitial fluid.
So that's based on the blood has a glucose and some enzymes. So that's resident in skin, for example, interstitial fluid, ISF, invasive or minimal invasive, you microneedle technology, and invasive is like using a laser. So basically the laser what we use is like let me expand to it. It's like NIR laser. So NIR laser is based on the A08 nanometer, or like we generally use this one because this one can penetrate tissue to around 2 millimeters, and based on the concentration changes. So this one, this laser will be absorbed with different efficiency. So use this way, we can as a biosensor detector.
Below the surface of the skin, and you can do it using needles, or it's called a wire sensor. I'll describe a wire sensor to you in a bit. I know that there's some people online with this video who are interested in microneedles. So you can also measure glucose in the interstitial fluid using microneedles. You can also do it, the holy grail of measuring glucose, maybe in wearables, is non-invasively. And so this is a company that's no longer around. They tried to do it through Raman spectroscopy. So everyone's got this dream that they're able to shine some sort of light through the skin and detect the glucose that way. So a lot of people have tried it. So C8 have tried this non-invasive way. Apple have tried it the non-invasive way. There's currently a company, I think, called Movano, who's trying to do it through radio frequency. It would be great if these techniques were working, but so far nobody's managed to pull it off. And if you're interested in making a non-invasive wearable glucose sensor, look up this URL, nivglucose.com. There's an interesting article. The guy updates this article every few years, and he does. It's got the title "Hunting the Deceitful Turkey," so it's worth having a look at that article. It's fairly well known among us who are interested in glucose monitoring. Just to touch very briefly on the wire sensor. If you want to know a lot about glucose wire sensors, then I would look at we got a product called CGM sensors, CGM wire sensors.
So that's the generous Y sensor. So with wires. Another one is wireless sensor. So if you implant the body, you need to think about how to change your signal to wireless. So generally, we have a module you can order it from Amazon or eBay or some Texas Electronics.
The nice thing about this kind of technology is there's nothing new here. The picture that's slightly hidden by my face is a guy called George Wilson, and the paper that I have referenced up here, Progress Towards Development of Implantable Sensors. He published this paper in 1992, so that was before I went to university. So it shows really that there's nothing new here. Now we do a version of his sensor, so we have a sort of platinum wire.
So this one is a pretty sorry. No. This one is pretty traditional way always, like for a pH meter right now. But the mechanism is pretty similar with the advantage of the manufacturing and advanced in the materials technology. So excuse like this one is a silver or silver chloride as a reference electrode. And another one is a working electrode. Could be your homework. Did you guys remember use PT? And we can also use like a carbon or graphene electrode together, put as a working electrode. They're working together to get the pH signal, pH to detect the pH, for example.
Contain electrochemically active molecules, and phenols, I believe, are in there, and they might be electrochemically active. So the question is, can I both deliver insulin from what's called a patch pump and measure the glucose at the same time? So they have a feedback loop. The concept is called the artificial pancreas. And the answer is you can do it. You just have to really think about the sensor and make sure that the sensor is not detecting other materials that are electrochemically active in the insulin solution. And I have thought about this, and I probably have some of the answers to that question. Now, one of the grandfathers of a wearable continuous glucose meter, some of you guys who've been doing this as long as I have will remember the glucose watch. It was a business in part led by a guy called Russ Potts. And in that, he was using a technique called iontophoresis, where he's effectively applying voltage and drawing the interstitial fluid through the skin and then measuring it externally. It was a nice concept. They did get it on the market, but they didn't stay on the market. But that would be the kind of grandfather of probably wearables, or a lot of wearables. definitely one of the grandfathers of wearable biosensors and actually the grandfathers of continuous glucose monitoring. Here's some honorable mentions of people who have tried to make wearable continuous glucose monitoring. Echo Therapeutics had a really good effort at it. Echo, they were actually abrading the skin. So they were literally trying to rub a little bit of skin off the surface and let the interstitial fluid then come through that way. I mentioned C8 earlier on, who were trying to do Raman spectroscopy. I mentioned Apple earlier on, who were actually trying to do, they're basically trying to use infrared signals. And I suspect it's because on the Apple Watch, there's plenty of LEDs here, and they could use those LEDs. And just breaking news, I saw that Apple last night did a press release where they're now able to measure oxygen levels using the Apple Watch. So I suspect basically they're...
So one thing's like to detect the glucose differently using interfacial fluid. So that's a fluid you need a micro needle, make a draw. And they use this one. Another one's like using, as I said, the AO8. So that's the Apple put together into to detect the oxygen. I know right now market a lot of device you can detect the oxygen, if specifically after COVID-19 or in the pandemic. So you can detect the oxygen and concentration and what for examples less than for examples like heartbeat and together. But the mechanism is like using NRR, AO8 nanometer laser, because the blood from fresh red to a little bit black, that's where, that's like for the black ones, go to a little bit dark, for example. NRR absorb with the dark color materials with more efficiency. So that's like reflect is different. So that is the mechanism.
The LEDs to measure the percentage of oxygenated and deoxygenated hemoglobin. Now, everyone thinks that Google invented this, this wearable contact lens for measuring glucose basically in the eye. I think that technology was old by the time Google had picked it up. So Google have also had a go at wearable biosensors. And there's a company here called Glysense who are making a much more invasive type continuous glucose sensor, and they are still operating. Sensionics is definitely worth a mention in this market. Then most of the biosensing I like to talk about is electrochemical. A, because I'm an electrochemist, and B, because it works. And probably C, because actually, if you want to make a low-cost sensor, electrochemistry is a good science for it. But Sensionics aren't doing electrochemistry, so I have to mention that. Their CEO, Tim Goodnow, actually was one of the... there's a technology owned by Abbott, and Tim Goodnow sort of ran that business for several years, so he has a background in this kind of science. But anyway, their technology is a long-term implantable.
So here I need to give you guys a little bit explanation. So generating the biosensor, another levels is like more even smart. It's like using A plus, for example, it's like A is you want to detect. So you can coat enzyme. Enzyme is a protein onto your sensor generates electrode. So if A come out, you want to detect, then specifically will react to an enzyme, because this enzyme is only react with A. So if A come out, so we form the B. So if B happens, then from electronic, we call the redox. Then this one change. So the voltage change, then we get the signal. So that's a kind of mechanism.
it's basically using LEDs to detect the glucose there. Right, I am going fast. So the big three in continuous glucose monitoring are Abbott, Medtronic, and Dexcom. For many of you, yeah. So Roberto Orbitz is just saying as well online that that's that contact lens that Google picked up. Yeah, it's much older than it was around a long time before Google picked it up. But anyway, the big three currently on the market in CGM are Abbott, Medtronic, and Dexcom. So Shirley asked a question online earlier on about whether we could measure glucose and deliver insulin in the same patch. And that's quite nice because Medtronic have that type of system. They don't have it in the same patch. They basically, on the torso here, they're measuring the glucose using a CGM sensor, and then they have a pump delivering insulin. And when those two things are, when the sensor controls the insulin, then that's called closed loop, and that's called the artificial pancreas. That's the term for it. Abbott, at least in Europe, everyone perceives them as being, one of the better glucose sensors on the market. And then we also have Dexcom on the market as well, who are also significant players. Now, these three sensors all have three things in common. They're all transdermal. They're all electrochemical, and they're all wire-like. So when I say wire-like, I mean, they have kind of...
So transdermal means like... generalized, we have the skin, 2 layers. That's one thing. Yeah. Epidermal, we know, right? That's the dermis layer. So there's another specific materials. It's a keratinocyte layers on top of that's very thin. So this one generates some dead cells and very stiff and densely packed. So to provide protection of the skin. The transdermal drug delivery is based on you need to penetrate this part. Go to this way. That's what we call the transdermal. So penetrate the keratinocyte layer, epidermis, go to the dermis, but only a little bit to that dermis layer. So nerve or blood vessel never really touched with the needle. So that's that transdermal drug delivery. So you will not, so not painful. Okay, that's good. For the lots of people.
Electrons sit outside of the skin. Then there's the sensor itself is punched through the skin. They're measuring the glucose in the interstitial fluid. Now, Medtronic is what they call a generation 1 glucose sensor. If you're not sure what a generation 1 glucose sensor is, I'll touch upon it briefly, but it's a generation 1 glucose sensor. Dexcom's a generation 1. Abbott relies on a series of papers and patents by a guy called Adam Heller. He was at the University of Texas.
For glucose sensor. For glucose, like the continuous or like glucose monitoring. You guys, if you are interested, want to like have want to set up a company and to do this one work, I could provide help. I have quite a few ideas. And right now on the market, majority valuable sensor For what? For diabetes. So diabetes products are a huge market. Yeah, in Manitoba, in all Canada, in around the world, North America. So whenever like you can use a test paper, using a sweat, using a microneedle technology, is a huge market. You can get a lot of chance get investment from venture capital. So let me know, yeah, if you're interested for to advance this technology.
There are lots of companies who are quite interested in making what's called a generation 3 sensor. So a generation 3 sensor uses an enzyme which doesn't have a mediator. So in a generation 1 glucose sensor has oxygen as its mediator. So oxygen is interacting with the glucose. In a generation 2.
So this one is about like a glucose. It's about enzyme. Yeah. Enzyme. Yeah. For redox reaction.
So you have a mediator. It's another molecule that's able to shuttle electrons from the glucose. I don't know why I put lactone there, but from the glucose to the enzyme, from the enzyme to the electrodes, you have a mediator. In a generation 3 sensor, the enzyme doesn't require a mediator. It's transferring electrons directly to the electrode.
So if you take a look at this one, GOX, yeah, that's an enzyme. Yeah, a glucose enzyme. And they can, if like a glucose concentration change, they can have a reaction. So general reaction, some voltage change.
And I'm going to try and get through CGM quickly now, because the directions for CGM, everyone would love to do non-invasive. And I've mentioned C8, Apple, and Google. So you can kind of see the kind of billions that have really been thrown at trying to do non-invasive glucose measurements. I think in reality, minimally invasive is really where this is going. And minimally invasive to me means microneedles. So you've minimally invasive, we've had GlucoWatch have a go at this, Echo Therapeutics have had a go at this. Sano Health, they're a little hard to find these days because I think they're in hibernation at the moment, but Sano Health have tried microneedles. And BioLink, they're the easiest guys to find online who are doing microneedles.
So
yeah, so I'm just checking a few slides.
So by microneedle right now also is 3D printable. That's good. Yeah, very good. Yeah. And right now it's like we like put micro. So every other chips or wireless or Bluetooth module you can order from Amazon or eBay and Texas Electronic for example. What right now the only way is like how to design your electrode and what materials, what enzyme you use. So that's it.
It's probably just worth saying that the reason we can talk with some confidence on on glucose and biosensors is because at Zimmer people, we do have a lot of on-the-shelf biosensors and biosensor formulations. You know, we're measuring everything from oxygen to garlic, from nitrate to chili. So we have quite a depth of experience. We also have quite a depth of experience in terms of we sell microneedles on the website, and we also have the electronics on the website as well. And we also have a sensor and a sweat patch configuration as well. We do think that, you know, nobody likes to give blood. Nobody likes to actually, people don't really like having their skin broken in order to get at the interstitial fluid. So it would be lovely if we were able to measure things in sweat. So we do have pre-existing on-the-shelf technology for measuring things like the sweat. I just want to make a quick comment as well about the electronics. So at ZP, we do have the electronics. I want to just make a couple of honorary mentions. There's a chipset from Texas Instruments. I want to say the MSP430. It's a classic chipset. It's used in a lot of glucose meters. So we are familiar with that. But these days, analog devices have also done a really nice chip-sized potentiostat. So if anyone's thinking about developing electronics for wearable biosensors, then I would check out some of the links on our website, especially this GFET, because there we do reference the chip that we use in one of our devices, and that's my recommendation for a small size potentiometer. Right, so now we're going to go to a demo. So what I'm going to do is I'm going to stop sharing for a second. I'm going to mute myself, and Andre and Mots, you'll suddenly see their faces appear, and they're going to do a quick demonstration for you guys. So I'm going to mute.
Yeah. Can you hear us now?
Just a sound check. I can hear you fine, yeah.
That's excellent. All right.
Perfect. Okay. Welcome to the live demo. So at this moment, we are going to present a small, before we show the potential of using it as a wearable, we are going to show you a small bench top on one of the, so this is a flexible circuit in PET film printed. So on here, we have to, in order for it to work, we need a battery, and we have like a flexible battery as well.
So this one,
you can even bend the battery.
that one just mentioned right now is like for at least in my lab, we are working on like a self-powered device. That's very important. If you implant the body, if you want your device for long times, so I would ask you think about to design a self-powered device. For example, we use a piezoelectrometers to collect the energy from heartbeat, from your movement. So that's the reason. For example, so we apply our biosensor onto a green agriculture. We can patch onto the, on the apple, on some tree leaves, the corn leaves. They can connect the energy from what? From wind, from snow, from sound, from raining drops. So we use this way to collect the energy to power, to drive the sensor works, to send the signal to your cell phone or to your computer.
So it's pretty flexible, and we need, of course, in this case, we are using as an example a glucose sensor. So so the objective of this glucose sensor is just to show you a signal. The signal, this is connected via Bluetooth, so it has an antenna, and it's connected. You have the board populated, and it's connected via Bluetooth to my computer. And so the objective here is for us to give small samples of glucose, and then observe just a step response in this live demo. So on this red bit that you see is just a connector adapter. It's just a 3D printed part adapter in order to hold the sensor in position. So in this instance, I'm going to take two different calibration solutions, glucose calibration solutions. You can see on the background that it's already communicating. I have it running at a potential of 650.
So that's like all based on potential of voltage. So they need a kind of calibration. So what like glucose concentration, for example, is like 1 macromolar or 1 milligram per milliliter. We have like 20 millivoltage or 200 millivoltage. So you can get a linear line, and each line then input to your laptop or software. So once like your sensor works, they will send out a voltage signal. So from voltage signal, the computer program automatically calculate to make it correlate with the calibration line. Then you know what is the glucose concentration in the body.
Millivolts, and I have a sample rate of 5 seconds, and and yeah, so I just want to. This is not an excuse. It's just to let you know that it's kind of hard. I can't on this interface. So this is the readout platform. I don't have control at this moment over the scale. So it might be sometimes hard to observe, but that's just the way it is. So
I think Andre can read off the numeric value, so you can see if there's a step change.
yeah. So at this moment, I just added a small glucose concentration onto the electrodes of the sensor. So you did see a step change. The sensor has become wet. So we are going to wait 1 minute, and then we change to a different concentration. So
So when I look at that data, I mean, I can see that it was going along in the baseline, and now it's sort of stepped up to a new place.
yeah, so it was dry. So what you see is a typical amperometric curve. So it went up, and now it's going to stabilize at a value. And so once it stabilizes at this value, then it's reading, and then I can try to do a step change. So so the problem is that the sensor first was completely dry, and then we wetted with solution. So so I'm just waiting a little bit, 1 minute, for the value to stabilize, and then I will change solution. So I will change
I mean,
solution
it's a bit of a plug from us, but I mean, it's worth saying. I mean, those glucose sensors and even those test solutions and that board and that battery. I mean, they're all just off-the-shelf items for us. You know, so we have. It's not like Andre had to make these things for this demo. These were things that he just, you know, we have them on our web store. So,
yeah.
So I agree with you, Andre, that if people are not sure why the data looks the way it does, this is what they call the kind of Cottrell response. So he had a dry sensor, he added the glucose, it spikes up, and then it kind of comes down, it drifts down towards this plateau. So yeah, sorry, Andre.
No, that's correct. So in this instance, we are using like an off-the-shelf sensor, glucose sensor, and I just want to mention as well. So we are doing a bench top, but everything here is flexible in a way. Most parts, except for the ceramic sensor, but we also do these sensors in PT films, and if once you attach it to the body, so the objective is to the forearm or the back. So the objective is to you attach it to the body. It could be your forearm, or it could be on the back, on your back, for example, or in your forehead, and you can use basically anything in order to that feels comfortable. Just a small band. You can't even see the sensor, and so it's there in order to sample it properly. And Martin showed very well in his slides. So the sensor should have a small microfluidic channel, and that will suck the solution for capillary forces into the sensor electrode area, which is the sensing part of our sensor. So I think we waited long enough. It's now stabilized, and what I'm going to do is with a tech paper, I will dry the solution on the top of the sensor, and I will pipette a different solution into it. So just bear with me for a second. I'll try to do this. So I'm now taking off the solution, and
I do appreciate the camera work by Mott's here, doing a nice job changing the angle.
so
You're welcome.
so now I have increased slightly the glucose concentration. Again, I can't. It's just the way it is. I cannot change the scale. But
yeah,
there
you can
is.
see it's higher, yeah.
Yeah, there was an increase of about 5 millimolar, so which is what we have here, about 5 millimolar increase of glucose concentration. So I hope this is more or less helps visualizing the how it can be. And any questions about this demo or any special observations or things that you would like to see in the next demo, please let me know, let Martin know, and we can try to include them on the next.
Brilliant. All right. Well, thanks, Andre and Mart. I do appreciate that. So, so I'll just check the time now. So we've got sort of 20 minutes left, but we'll try and finish up early. So, so what I'm going to do now is carry on with the thank Mats and Andre for the demo. It's very nice. So they started with a dry sensor. They pipetted on some glucose solution. It spiked and then it relaxed, and then it came to a new signal. So what we'll do now is, now we have talked a lot about glucose this morning. I sort of apologize for that. Roberto Orbitz asked whether we need to calibrate each sensor before use. The quick answer is we'd hope to do it in the factory, because we can't expect real customers or real patients to be doing that. So no, so we're not expecting that. Now, what Zimmer Peacock is doing is we have a lot of standard products, and so we're really trying to help academics and entrepreneurs get to market quickly. So we have a lot of off-the-shelf technology, but these things still need to be put into the right form factors in order that they actually become medical products. So other analytes that I want to mention this morning, I don't want it all to be dominated by glucose. So people are focused on glucose. Other things that people are very interested in is lactate. Cortisol is, we get a lot of inquiries around cortisol. I think hydration is really interesting and quite doable. And, you know, maybe there's an interest growing in actually the continuous measurement of sodium and potassium, potentially for dialysis patients. I think at the moment, dialysis patients are kind of called in a sort of routine fashion, rather than sort of when they need their dialysis, they're just called in just on a schedule. So it'd be nice to be able to be a bit more accurate in calling in people for dialysis. Potentially measuring the sodium potassium could be an interesting way of doing that. Some honorable mentions. L'Oreal actually did a nice wearable biosensor. It wasn't electrochemical, it was colorimetric, but I did like it because it was wearable. It used some microfluidics, and it was apparently measuring the pH of the skin, which makes really good business sense for a company like that. And it also kind of went nicely because before that they'd actually done a light sensor. So I do like, you know, the innovation coming from this company.
So this one is like a pH values, not only detect the inside of the body, because the stomach pH or intestine pH, in the small intestine, the pH is more basic, around 7. But the stomach go to the pH go to around 1. And they are all pH changes with it. Yeah, that's the kind of like a symptoms of some disease signal. And the same as the skin. So in the general, the skin is a little bit acidic. Yeah, sometimes could go to a low as low as 6, around 6. And however, like if the skin unhealthy or something happens on the wound, so the pH will go to around 7 or 7.2. So a good health is not like neutral. It's a little bit acidic. Yeah, 6.8 for example. That's good. And so here's like sensors, like using 2 electrode or 3 electrode, attach onto the skin, and because different pH means like different ions or like protons concentration change, then we can detect the voltage or some voltage change, for example. So use this way we can give a monitor or real-time monitor the skin or the organs, like by robot.
There about this, and they also think that light is important to, you know, as a damaging factor on skin. So they also have a little light sensor for it. So that was kind of cool. hydration, there's a couple of companies out there playing or working on hydration. There was one company seems to have changed its name or been bought. They were called LVL, now BFX, doing a hydration sensor, and then another company called NIX. So it's not just all about glucose. Other people are out there working on things like hydration. Some mentions. I was going to keep away, and I am keeping away from things that are not really not biosensors in my definition of the term, which is chemical and biological analytes. But Philips, for example, have done this ECG wearable sensor, and Empatica seem to be doing a sensor for helping with neurological research. This one I really quite like. Again, I am trying to keep it to chemical and biological biosensing, but I want to give these guys an honorable mention. They're called Athos. There's a technique out there called electromyography, which has been around for decades, where you effectively measure the electrical signals from muscles as the muscles are working. And Athos have basically taken that kind of technology and just implemented it into wearable clothing. Into clothing, which is obviously by definition wearable. So I think Athos are making a really good job of this. And I mean, from their own website, I can see that literally they started with sort of standard electromyography, and they've just made the form factor much nicer. And Athos is a good example of, taking something that's probably already done and quite robust in terms of electromyography, but putting it into a cool form factor, wearable, suits. The electrodes for measuring the electrical signals from the muscles are probably buried in that suit or in the clothing. So that's a nice example of a wearable sensor. It's not strictly speaking a wearable biosensor. Now, the academic literature, there's lots of people out there. I wouldn't say it was dominated, but one of the most highest outputs in this space is a guy called Joseph Wang. So when you look through Joseph Wang's papers, he does have.
So Joseph Wang is like one of the most kind of work, not only by sensor, it's by robot. So I will like in the next few class, we will present his work, and his lecture in the Harvard University is pretty good. And each case I will experiment on them specifically for by robot. And in front of the mini robot, his team developed quite a few nice things like self-powered using H2O2 and to drive, or like use the PT and make a redox reaction. So here's one example as a biosensor. And I must stop here. So any questions? Any questions? Yeah, just like don't forget this part of homework. Okay, this Friday, not due date, but I wish like you can submit me by and a little bit suggestions to your project. If no question, our class is over. And if you have,
I have a quick question.
sure.
We won't have a tutorial on Friday, correct? Because it's a holiday.
Yeah. Oh, really? It's a holiday.
Yeah.
Oh, thank you. Let me know. Like, so it's possible, like Thursday, for example, Thursday afternoon, or like you guys, or like some other time. Yeah, can your team send me your proposal, this part, then I give you quick comments and then send it back to you. Is it okay with you?
Like to email?
Yeah, email to me first. Then if we can figure out a time for discussion, then we can use a Zoom. But send me the email is okay. Yeah.
Okay.
Yeah. Thank you. Yeah. So good. Yeah. If no comments, questions, just say goodbye and waiting your proposal. Thank you.